Hello. So this is my demonstration of my final project. Um, all right, let's start from the beginning. Okay, so first of all, I want to explain that this notebook is actually inconsistent. By that, I mean I demonstrated my initial version of project to the TA, where the approach is straightforward. I used single zoom level to train the model without any data augmentation, and also I used um, accuracy as metric. So the I that was a complete flow, but it's not. I think it's not good enough. So after the demonstration, I took some advice from the TA, which is to use data augmentation um, to fight. I'm sorry, to avoid this huge imbalance of data. Also, I was gonna improve on. Uh, I was gonna use multiple zoom level to train the model and to use F1 score as metric. But for some silly reason, I didn't save my initial version of Notebook, so I just changed my code on the on this notebook. But I was stuck on I got stuck on the training part, and I couldn't get things straight in time. So I'm so sorry for that. Um, but I still did data augmentation and built the model, a slightly complicated model using functional API. So I hope I can still explain, what I did. But just to make things clear, that the first part of this notebook, up until the training section, it is all the code are intended to train a multi zoom level model that use data augmentation. And after the training part, the result actually comes from my initial model. So I hope I can explain that. And okay, let's start it. That's just to install all the packages. And okay, the first thing we do is generating the training data. Obviously, here we use level 3 and level 4, and this is the downsample factor of level 4, 3 and 4, which is 8 and 16. So here because we classify a patch based on the center area of that patch, whether it contains tumor or not. So for that area, I wanted I wanted to shift that area in this stride. So this stride is 128 times the down sample factor of level 3. And the threshold here is actually the minimum tissue percentage um, that we want in our training data set. So all the patches that have tissue rate lower than 10% will be ignored. That's just the dimension of the patches and the center region. Okay, so these are some helper function that, so this helper function is provided by the professor, and the rest of the helper function are wrote to extract patches and calculate tissue rate, um, stuff like that. So for get patch and label, this function is uh, perform perform the actual extraction behavior. So you can see that given the tumor slide and the mask slide, so anchor here means the position of the center of the patch. So based on that, we calculate, you know, what are the areas that we need in our patch. So after we extract the patch for both levels and the mask, so the mask is on the same level of patch. I'm sorry, on level 3, which is the higher level of resolution. After that, we calculate the tissue rate of both level 3 and level 4. So we only include those patches where the tissue rate of both level is more than 10%. Otherwise, we ignore those. And this helper function called extract patches here is actually a wrapper of all the previous functions. So given a tumor slide and a mask slide, it's going to return all the patches in this slide, all the valid patches. So you can see here we call here we have the anchor, and we slide this anchor across this whole slide. And for each position for each anchor, we call get patch and label, and so that we could actually extract that patch. All right, and then let's prepare our data. So the data is actually very, very large. The tumor slide is actually around 1 gigabytes. I think I actually have one that is around 3 gigabytes. Yeah, there you go. So yeah, let's first download it, and then let's actually generate the patches. So we iterate through each slide, and we're going to call extract patches, and that's going to generate the patches and the labels. There are actually a lot of patches, but most of them are invalid. By that I mean it doesn't contain enough tissue, or it doesn't contain enough tissue. So we can see in total we have more than 5,000 patches, we have more than 5,000 valid patches, but we only have around like 126 cancerous patches. So this is just a summary of the total patches in each slide. So for the first slide, we have more than 19,000 patches, but only 2,000, less than 3,000 patches are actually valid. And that's, same thing for the second slide and the last slide. For the last slide, we actually have around half of the total patches are valid. So anyway, altogether we have around 5,000. We have more than 5,000 patches, but only 126 of them are contains cancer. So that's a huge imbalance. The solution to this problem is data augmentation. Here I saved the patches to disk because they're huge. And actually, during all the experiment that I did, Colab runtime constantly die on me, either because of I exceed the memory limit, or for some other weird reasons. But yeah, it actually really time consuming. So to avoid exceeding the memory limit, I only use a subset of all the patches that we generated. So that's why I have a lot of save and load here, just to reduce the memory use. I can just save part of the patches onto the disk, and then restart the runtime and only load that subset. So we don't have a lot of patches that we don't want to use in memory. And let's take a look. So these are the pictures appear in pairs. So the one on the left is in level 4, and the one on the right is in level 3. So this patches actually contains tumor, and this doesn't. So the next thing to do is data augmentation. So we use the image data generator. So we apply, some rescale, rotation, shift, and zooming. So here we decide to only use, a very small subset of all the patches that we have. This is actually this is to perform the actual data augmentation. So to control the number of augmented data that we can generate, I did this in a manual way, so that we can control the number of augmented data we have. So in the end, we would have, we would generate around 200 patches, more patches for each level. These are all new, so, and yeah, we can see we have 190 augmented patches for both L3 and level 3 and level 4. Let's take a look. So yeah, these are the result. And to combine them with the original data, we take only 500 non-cancerous patches. So altogether, we have a little bit more than 800 patches that we can use as our training data. And let's shuffle them. So then we can start building our model. So this is the part where I got stuck. So I wanted to build this model where it takes two inputs, the level 3 and level 4 patches. So I did a little research on this. So I think the recommended way is to use this so-called functional API. Yeah, and the way to do it is to have those input layers and concatenate layers so that we can concatenate different inputs. So for each tower, we have this convolutional base, we have dropout, we have dense layer. So for the convolutional base here, we use VGG19 and 16. This is a little weird. So VGG19, I try to use only one of them, but it gives me this error message saying that I have duplicate layer names, and I couldn't figure out a way to change that, to avoid that. So to avoid this problem, I just use another model because I think VGG19 and 16, I think they're pretty much the same. So I don't think this will matter that much. So I used VGG19 for level 3 and 16 for level 4. Then we concatenate both tower together and output a final classification. This is a little summary of the model. And here is our error message. It says I don't have compatible shape between the logits and the labels, which I'm not sure why. I'm sorry, but I couldn't figure this out in time, so just let me explain the rest of the notebook. So in the initial version of the notebook, which I demonstrated to the TA, and I don't have it right here, this is the training process of the initial model. It looks all right, but it wasn't carefully, you know, designed. We would, it's without data augmentation, and it has huge imbalance of data, and also we don't have as many patches as we have here. And then that's the test part. So I download another new slide, and let's take a look. And that's the new slide. And I'm sorry, this function is not used here. Right. Then we do the same thing. We extract the patches from this test slide. This is just to extract patches on along the right edges and the bottom edges separately, so that we have all the information. And then we perform. First of all, let's take a look. Yeah. And finally, we evaluate our model. And we can see the test accuracy is around 90%, but it's not very convincing because, we have this huge imbalance of data. Anyway, after we have our predictions, we can generate the heat map. So when we were extracting the patches here, it's actually a little different than the training process because I add this position information here of the anchor, the position of each patch. So with that information, we can recover, we can generate this heat map using the prediction that we have. So this is a helper function that I wrote to fill the mask region if this region is classified as tumorous. And this is actually the the generating process. Yeah, with all the predictions we have, if this region is classified as tumor, meaning label here is 1, then we fill the corresponding mask. So we have the mask here, we have the position here, and the size. And let's take a look at the final result. So we can see some of the tumorous regions are correctly classified, and then we have some other wrong prediction. But this is not very, very convincing. But this is the initial result that I had, but not the, the ideal result. So this is pretty much all of my notebook here. I know it's kind of confusing, and I actually didn't complete this final version, but I still tried to let you know what kind of work that I did. I hope that I explained everything. And yeah, that's it. Thanks for watching.